Brings us to a question. These examples come out of section 11.1, permutations. In this question we're asked how many different four-letter arrangements we can make of the letters A, B, C, D, and then in the second part AABC, AAAB, and AAAA. We could start with the bottom one, AAAA. There's only one way to do that. You change an A for an A and you've got the same arrangement, so you've got 1 is the answer to this last one. So let's talk about ABCD. By this point you probably are okay with that being 4P4 or 4 factorial, 24 different arrangements. And if you're in class, I wrote, A, B, C, D, A, B, D, C, and every other of these 24 arrangements. We can keep going. Etc. So I won't spend all your time writing down all the arrangements of A, B, C, D, but you can believe that you've got 4 spaces. For the first space you have 4 letters that could go there. Once you've used one you're down to 3, then 2, then 1. So 4 factorial of 4p4 equals 24. Now when I try AABC, what happens is I end up, every time I switch an A with an A, I end up with the same arrangement. So I do have still a number of different arrangements. But not quite as many as I had in the last one. And try as you might, you've got 12 arrangements exactly, which by no coincidence is exactly half as many as when the letters were all different. Now if I try AAAB, I don't need to pause the pen because it only takes this long to write all the possibilities. That B basically can go in any one of the 4 spots. So you only have 4 arrangements. As I said, the first one, when the letters were all different, the answer was 4 factorial. As soon as I had 2 repeated letters, we actually had 4 factorial, but divided by 2 factorial. When we had 3 repeated letters, we had 4 factorial over 3 factorial. And finally, the last silly example, we had 4 repeated letters, 4 factorial over 4 factorial, which gives us our answers of 1, of 4, of 12, and of 24. So what happens is when you have repeated objects, and you're trying to arrange them, you have n objects altogether. You start with n factorial, but however many repeated objects you have, you say, I've got this many repeated of A, this many repeated B, this many repeated C. So let's do another example of that. So we're asked how many arrangements would there be of all the letters in mathematical. Now that's a big word, you've got to count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we start off with a 12 factorial. If all the letters were different, the answer would be 12 factorial. But if I take a closer look, they definitely aren't all different. I have M here, M here. So divide by 2 factorial, because every time you switch an M with an M, you take away half of your arrangements. Now look at the A's. I've got 1, 2, 3 A's. So 3 factorial, because there are 3 factorial ways of arranging 3 letters. Every time I switch an A with an A, I've got the same word as I had before. It still would spell mathematical in this instant. T's, I have 2 T's as well. And so I look at the H's, the E's, the I's, and the C's, and the L's. There's only one of each, so this would be my final answer. Still a huge number, but not quite as big as if I had 12 totally different letters. Specifically, the answer, instead of being 479 million, ends up being just about 20 million. The answer here, if you punch it all in carefully into your calculator, 19,958,400. Still plenty, but if I had the letters A, B, C, D, E, F, G, H, I, J, K, L, 12 letters would be, like I said, almost 500 million instead. Brings us to a question that looks totally unrelated, in that it's a pathways question. It says, how many pathways are there to go from A to B if there are no reverse moves possible? Now you could try counting these, and you'd say 1, 2, 3, and try to keep track of them, but it gets quite difficult, especially if the grid gets a little bigger than this one. But hopefully everybody will agree that to get from A to B, I need 3 moves to the right, and I need 2 moves down. and any order I put those in will end me up at B. If I go down, down, right, 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 or right, down, right, right, down, I'll still end up at B. So the answer to this question, if I relate it to what I just did above, would be 5 factorial divided by 3 factorial, 2 factorial. Turns out, in this case, the answer is just 10. Not a huge answer, but if you make this grid bigger and bigger and bigger, you can get hundreds and even thousands of pathways. You don't want to have to try to trace those all by hand and keep track of which ones you have and which ones you haven't counted. So these pathway questions with a simple grid are not too bad.